Go back. Rainbow Bridge. So you see this right here. This is an arch. This is out in Utah near what's called Lake Powell. Maybe some of you have been out to Utah. I have not, but you might have see these kind of features out in places like Utah. This is where it is, up here in the north part of a mountain called Navajo Mountain. So I'll read. It says Navajo Mountain is in southeast Utah. It's a dome-shaped chunk of igneous rock that intruded into sedimentary layers and lifted up the overlying layer. Navajo Mountain is one of several of these. They're called laccoliths. And this next picture will show what a laccolith is. So you have up here on the top, these are sedimentary layers, and then down here below in this section is magma, which is going to form your intrusive igneous rock. This magma will keep filling in and eventually causing these sedimentary layers to buckle and cause them to bend up like this to create a mountain. So it's not done with plate tectonics, which is a very common way of forming mountains. It's done with just a big plume of magma underneath the ground. It takes these sedimentary layers and kind of pushes them upward like that to make this mountain. So laccoliths are one way to do it. Anything lith, remember, let me clear that. Lith means rock. And so you have laccoliths, and then down here they're called batholiths. A batholith is a huge amount. You can see the difference in the magma. You have some magma, but then when you look at a batholith, that's a huge amount of magma, even much, much, much bigger. Very famous batholith, which we'll talk about, I think, down the road, is Mount Rushmore. So Mount Rushmore is this huge mountain of granite that was underground and is now sitting above the ground. But that's what they carved the president's faces out of. All right, moving on. So weathering is, this is definition, the breakdown of rocks into small pieces. Those small rock particles are called sediments, which form, of course, sedimentary rocks. Like these are your sediments: pebbles, sand, silt, clay. Let me go to the reference table real quick. So this is on page 6 in the reference table. It's in the top right corner, and they list the sediments by size. So if you look at these numbers here with these dotted lines, that gives you the size for each of these sediments. So for example, in order to be a pebble has to be technically anything from 0.2 centimeters up to 6.4 centimeters. And you see it tells you right here, particle diameter. That's on the y-axis. So a pebble is anything from 0.2 of a centimeter up to about 6.5 centimeters. So again, any rock can become a pebble. I can take a great big boulder, and technically a boulder is anything above 25.6 centimeters. I can crush it down with a hammer and make it into any one of these sizes below it. So any rock above 25.6 is a boulder. Anything between about 6.4 and 25.6 is a cobble. And then you see as you go down the list. So clay, which is very, very small, microscopic, has to be 10th, 100,000, 10,000. 4 10,000ths of a centimeter or less to technically be clay. And so these are your sediments, and that's what weathering is. It just breaks rocks down into any one of these sizes. These are the three things that will break down rocks. Number one is water. I mean, the earth is 70% water, your body is 70% water, or something like that. So water, which I always find very ironic, is essential to life, right? You need it to live, but yet it also destroys things. So that's your number one way to break down rocks. Air, oxygen, things like that is going to break down rocks. And then living things, when you have animals and plants that will burrow through the rocks and break it apart, or you have a tree that as it grows and the roots will bust the rock apart. You have mosses and lichens and algae, things that grow on the rocks that will also cause rocks to break down. So we'll get into all this stuff here as we move forward. But those are the three things: water, air, and living things. There's two types of weathering. And again, this you probably covered in middle school, I'm going to say, 6th grade again. You have what's called physical weathering. So physical weathering is you just break down the rocks without changing the rock. So you're not creating a different rock, you're just breaking it into smaller pieces. And the best example is what's called frost action. Frost action is ice. So let's say in the fall, right, you have a crack in the rock and it rains, the water's going to seep into those rocks, and then in the winter, when the water freezes, that ice is going to expand and it's going to break the rock apart. So the climate you need is always humid. You want water, so that's number one in all types of weathering. But in this case, you want it to get cold and hot. You want they call it the freezing and the thawing. And this video here is going to talk about that. Best example of actual frost action is potholes. So let's say you have your road outside your house and it's blacktop, and again there's cracks in the blacktop, and then it rains and the water goes into that blacktop. It's going to seep into those cracks. Then in the wintertime, that water is going to freeze. It's going to cause the blacktop to buckle and start to push up. Then when you get to this time of year, April, May, springtime, as that ice is melting, it's going to cause the blacktop to cave in, and then you're going to get giant potholes in the blacktop. So let me put this video on. Hopefully you'll be able to hear it this time. I think I figured out why I gotta mute my microphone, so let me play this video for you. This one's just on physical weathering.
Physical weathering is the actual breaking down of rock by the action of natural forces, such as water, wind, plants, and animals. But how do these forces wear down rock? Here we see trees growing out of what appears to be a solid granite rock. Actually, their roots are penetrating tiny cracks in the rock. As the trees continue to grow, their roots will further extend and enlarge the cracks, eventually fragmenting the rock, just as these roots have done to this rock. Probably the most common cause of physical weathering is due to the constant freezing and thawing of water in and around the rocks themselves. Let's take a look at a simple experiment which shows how liquid water expands when it turns to solid ice. We fill this plastic measuring cup with water up to the top mark. We want to make sure that we use a plastic container and not a glass container. We'll now take our cup of water and place it in the freezer. Here it will sit undisturbed for several hours. Later, when we view the cup, we find that the water has turned to ice and that it has expanded almost 10%. We note that it has increased in size both upward and outward and has actually cracked the plastic cup. But how does freezing water affect rocks? Water frequently collects on rocks and gets into their small openings. When temperatures drop below freezing, the water in these cracks turns to ice and expands. This exerts a tremendous amount of pressure on the openings in these rocks. As temperatures rise and the ice melts back into its liquid form, it creeps deeper into the fractures. When the water freezes again, it further expands the openings in the rock. This cycle will go on day after day, year after year, until finally a once huge mountainside could disintegrate to a pile of small rock fragments.
Okay, so that was on physical weathering. These are just some pictures of examples of physical weathering. Like I said, potholes in the road where you have that freeze and that thaw. It causes the road to buckle and expand, and then when the ice melts, it causes potholes. New York City, this is sometimes how they fix the pothole problem. So you have this giant pothole in the middle of Manhattan, and they'll just throw a bunch of cones in there temporarily just to warn people, as they go by, watch out for these potholes. But you'll see this very common, especially this time of year, springtime, when the roads are all in bad shape and they've got to go out and either fill these with some loose blacktop, some granular, they call it asphalt, and tamp it down, which doesn't always fix the problem, or they got to strip this entire road, take it all out, and repave it. That's a very common problem this time of year. Sidewalks will do this. Some of the sidewalks you see around Rhinebeck in the village, you'll see they look like this over time as the ice again gets in these cracks in the blacktop and breaks it apart. So you see that happen very often, and after so many years they got to go out and fix those sidewalks. This is frost action out west. I forget what state this was from, but you get this where it breaks apart the tops of these cliffs, and you'll see the rock falls happen, and after a while they kind of look pretty cool. Looks like a castle to me, but you get those like castle looking structures on the top there. This is not ice. This is done with wind, which is a form of erosion, but they call them mushroom cap rocks. So what happens is the rock might start out looking pretty straight and right angle like this. The wind will blow in from the east or from the west and start to eat away at the rock over here on the side and round out the top of these rocks, and you get these shapes eventually. If I draw like a finished product, will kind of look something like this, and they call mushroom cap rocks. So that's done by wind abrasion, as the wind is blowing usually 3, 4, 5 feet into the air, and it blasts away at the rock and starts to eat away at that and cause those cool structures. So you see that very common out west. I pick on A-Rod. As you know, I'm a Met fan, so you'll see as I move forward, I do put A-Rod in a bunch of my pictures. Sorry to you Yankee fans. So this is called root pry. Again, some of you have trees. Maybe you see trees on a sidewalk in the village of Rhinebeck, and as the tree grows bigger, the roots will go through the rock and start to bust the rock apart. So they call that root pry, right? To pry means to just pick it apart. So that was my A-Rod joke number 1. What happens when you have a rock fall, which again is very common, maybe not so much on this side of the river, but if you go across to the Catskills, Hunter, Tannerville area, Windham, if you go up in those ski areas, you'll see this time of year you tend to have a lot of rock falls. And so as the mountain at the top breaks apart and then that rock starts to fall down the hill, at the bottom of the cliff you'll have a whole pile of broken up rock fragments. They call that talus, or talus slope. So talus is just a pile of broken up rock after you have a rock fall. If you ever visit Yosemite National Park out in California, this is a very famous attraction. Again, I've never been. Maybe some of you have been there. It's called Half Dome. So this is, again, a dome-shaped mountain, but obviously half of it. And what it's doing, it's exfoliating, which is like onions. When you peel the layers off an onion. So this is going to keep peeling away layer upon layer upon layer. This thing's just going to keep peeling away. So that's a form of physical weathering called exfoliation. The other type besides physical weathering is called chemical. So here, again, you need water. So you want the humidity, you want the moisture. But now you don't really want cold weather. The hotter, the better. So the Caribbean islands, you're going to see this happen a lot. Florida, I'll show you some pictures of some sinkholes in Florida. A lot of your tropical climates is where you're going to have more chemical weathering. We're going to have chemical weathering, but mostly in the summertime, all right, because that's when it's the hottest and the most humid. So I have another video here. I'm going to pause my microphone and show you this video on chemical weathering.
The second kind of weathering is called chemical weathering. Chemical weathering causes changes in the rocks from the reaction of different chemicals on the surface of the rocks. One common example of chemical weathering is called oxidation. If we were to leave an iron nail in a cup of water for a few weeks, a chemical change takes place. The nail gradually becomes coated with a dark red substance we call rust. Rust is oxidized iron. Here we see the difference between a shiny new nail and an oxidized nail. This rusting or oxidation deteriorates any surface on which it reacts and will eventually cause it to break down and fall apart. The mineral iron is present in many different kinds of rocks, and oxidation can break down these rocks if they're exposed to water for long periods of time. But are there other ways in which rocks can chemically weather? These rocks are covered with a plant called lichen. They illustrate another example of how the chemical weathering process takes place. The lichen actually secrete a mild acid which can dissolve or eat away the surface of the rock. Carbonic acid, a mild corrosive agent, can form when water and carbon dioxide combine naturally in the air or below the earth. Underground caverns like this are one of the most spectacular examples of the effects of weathering caused by carbonic acid. This cavern started out as small openings below the Earth's surface where water seeped in. The water combined with carbon dioxide from decaying plant material in the soil to form carbonic acid. As this acid dissolved the rock around it, the pockets gradually grew in size. The force of gravity, combined with underground streams, carried the dissolved rock fragments away until finally a huge cavern was formed. This, along with the continuous seeping water, caused the cavern formations to grow even stranger as time passed.
Okay, so those are some examples of chemical weathering. Let me move forward here. So you don't necessarily have to remember the chemical formula. When you go on to take chemistry, Mr. Stevenson, he'll get into all this stuff. But you should know the types of chemical weathering. So one type the video talked about, that little short video, was oxidation. So you're taking rocks and minerals, you're mixing them with oxygen to create that rust. So your rocks that tend to have iron in it, or minerals. There's a mineral on the back of your reference table called hematite. If you look up the chemical composition of it, it's got Fe, which is iron. You take that and mix it with some oxygen, which is in water, and that's going to create a different type of mineral. So hematite will oxidize to become what's called a goethite. Again, you don't have to remember that, but just remember what oxidation is. Rust on a hammer, rust on a nail, rust on... I remember as a kid... and I'd be working outside and leave a set of sockets outside on the driveway overnight, and it would rain, and then those sockets would get rusty, and my father would get really upset and have to go and buy him new sockets because I ruined his socket set. So that's going to happen if you do stuff like that. Hydration. So hydra means water. You're mixing minerals with water. You take minerals like feldspar. You got your potassium feldspar and you plate clays feldspar. If you were to crush those down into a fine powder, I might have mentioned this in class a while back, but if you crush them down, mix them with water, you actually make clay out of that. So if you took the mineral feldspar, crush it into a fine powder, and put some water in there, that's what clay is. So that's, you're hydrating the feldspar, turning it into something different. And then carbonation. The video talked about rain mixing with carbon dioxide in the ground from decayed plants or the carbon dioxide that's in the air. And then that water with carbon dioxide makes a carbonic acid, which, if you remember from your rocks and minerals, the mineral calcite, some of you remember that, where you drop a little hydrochloric acid on it, will bubble. And so calcite is in two rocks in particular, limestone, which is sedimentary, and marble, which is a form of limestone. So a lot of your ground has limestone in it, and so when that carbonic acid, which is just rain with carbon dioxide, mixes to form a very weak acid, it's going to eat away at that limestone to form caves and even sinkholes. If you've ever been to Howe Caverns, that's how Howe Caverns form. So out there is a lot of limestone rock under the surface, and over time the rainwater, which was carbonic acid, mixed into the limestone and started to slowly eat away at it to form things like Howe Caverns. Florida, if you study the state of Florida, I mean, yeah, the surface is mostly sand, but what happens is underneath the sand on the surface of Florida is limestone. And so over time, what's happening is the limestone underneath is getting eaten away, and these have become like ticking time bombs where all of a sudden you create these sinkholes that happen very quickly, which can be very dangerous in places like Florida. I'll show you some pictures here. Here's one. So this was from June 2014, not that long ago. This was near Legoland, Florida. It was a big thing on the news at the time, but there was a house here, or like one of these, this house here was probably sitting here, something similar, and all of a sudden you had these sinkholes, and they happen without real warning. All of a sudden the ground just drops out like that. It's almost like an earthquake instantly, and the house just sinks right into the ground. And that's because down here in the subsurface is all your limestone. Again, over time, this doesn't happen overnight. This could take years and years and years. But as the rainwater seeps into the ground, it's starting to eat away slowly at the limestone. Again, the surface is sand. Sand isn't going to hold. So once the foundation underneath the limestone is chewed away, this sand is just going to buckle and cause the structure on top to collapse. So you get these very common, this happens a lot in Florida. This can happen on places like Long Island, where the ground is sand. Rhinebeck, we're upstate. We're not a sandy kind of soil, so it's nothing really to worry about up here in the Hudson Valley. But places along the coast, like Long Island, Florida, they definitely have to worry about sinkholes all the time. Acid rain, which is a form of chemical weathering. So this is just to show you the difference in what happens over time. So you take this picture on the left of this statue, and you can see all the detail in the woman. You can make out her hand. You can make out her face. This was made out of limestone. Limestone's a rock they use a lot in statues because it's very soft, and so it's easy to carve. Same thing with marble. Marble's a relatively soft rock. So when they use limestone and marble to carve statues, that's fine temporarily, but what you can see happens is if you go from 1908 to 1969, you're talking 60 years later, all that rain, acid rain, is going to start to dissolve away. And you can see there's nothing left. All the details have been destroyed in a matter of 60 years, which is relatively short time. Same thing happens if you go into like cemeteries, not that you want to visit cemeteries often, but if you go into a cemetery, walk around, look at headstones, you can always tell which headstones are made out of limestone or marble, because over time, let's say this is your headstone, and you have all that writing on there, who it was, when they died, etc. Over time, the acid rain is going to eat away at all that. It's going to get dissolved. Best thing to probably make statues out of and monuments and things is granite. Granite's indestructible. Nothing's going to affect granite. The problem with granite is very costly. So, if a loved one passes away and you go to pick out a headstone and you go to these places, they say, well, what would you rather have, the headstone made out of limestone or made out of granite? I mean, the limestone's going to be much cheaper. So if people that are on a tight budget or they don't have the money to pay for it, they're going to say, well, I'll use limestone. But over time, it's going to eat away the writing. You'd have to have it re-etched every so many years, or you're not going to be able to read it. If you spend the extra money and you buy it granite headstone, yeah, that'll last forever. You never have to worry about granite. The video talked about what happens if you go into Howe Caverns, right? And again, you might know this already. Again, limestone and marble, which are both made out of calcite, are going to be easily dissolved by that carbonic acid. And so when the drip marks come off the ceiling, that's the way I remember. I think, all right, like an icicle hanging off the ceiling is called stalactites. So a stalactite are these guys on the left where they're hanging down off the ceiling. And then when the drips start to build up, let's say this is the ground, and you start to put that dissolved limestone and it keeps building like this upward, those are called stalagmites with a G. So stalactites hang from the ceiling and stalagmites grow up from the ground. So on the left are your stalactites, and then these are growing this way off the ground. They're called these are stalactites, and these are stalagmites growing upward. Sometimes what will happen is the stalactite will grow down from the ceiling and the stalagmite will grow up from the ground, and eventually the two will connect. And I believe they're called a pipe organ or something like that, like you think of in a church. These are some very old pictures. My wife, her grandmother, who passed away several years ago, she used to have a summer home up in Vermont. It was in Heartland, Vermont, right along the Vermont New Hampshire border there. Quechee, it was called Quechee Gorge. Nice area up there if you go up to Vermont often. And so I'm one of these people. You'll see these people taking pictures of rocks and wonder, what is that idiot doing on the side of the road? Oh, that's people like Mr. Rocco who pull over and take pictures. So I was saw this as we were going up to my wife's grandmother's house way back in, that was 2002. But there's pictures you'll see over here where you see this grayish rock now turns kind of reddish brown color. I was taking pictures to show oxidation. This one shows it really well. So it looks like somebody splashed paint on the rock, but they didn't. That's all over time. That's chemical weathering, just showing the rust there on the side. There's some oxidation there. So if you have you're doing some construction or demolition, and you take some 2x4s and you got those rusty nails and you lay them outside, and then it rains over and over again until you get rid of this wood, you're going to see those rusty nails like that. Just be careful not to step on that. True story, I'll try to keep it quick. I actually stepped on a rusty nail, something like this, went right through my foot. I was probably like 6 years old and stepped right on it and didn't see it. Was playing around. I was at my friend's house and his dad was doing some construction and went right through my foot and had to go to the hospital, tetanus shot, the whole 9 yards. So pretty dumb. Yeah, we all do dumb things. There's different types of nails. So a lot of times when you're building stuff like that's going to be outside a shed or something like that, you're going to build a deck off your house. There's different types of nails. I'm not going to go crazy and read this whole thing, but there are what are called galvanized nails, which have undergone a process. They cover them with zinc. That puts a protective coating on them, so they'll be protected from things like becoming rusted. That's probably what people will use now. So if you go to, Home Depot, Lowe's, Williams Lumber, and you're going to build a deck, they might say, well, use galvanized nails, which have a special coating on it to protect them from the elements like oxygen and rain and stuff. I remember this show used to be on MTV. It was called Pimp My Ride, so this was supposed to be a joke. Unfortunately, we weren't in class to get your reaction, but yeah. So I remember this rapper, his name was Exhibit. So he used to take those old rusty cars, and he used to pimp them out and turn them into like fancy cars. And they would all be rust buckets. He'd buy them for like $200 and turn them into these cars worth a lot of money. So that was like the before picture and then the after picture. So I used to love watching that show when I was younger. It was kind of cool. Weathering is actually the beginning of the process of soil. So if you go outside, right, and take a shovel and dig up some dirt, you're about 50%, and we'll get into soil probably later this week. That might be my next video. Soil is made up of almost 50% rock particle. You got your other stuff in there, organic material, you got water, you got air, but 50% is the broken down rocks. So weathering is the beginning of the process of forming soil. So again, if you go back to day one, Earth didn't have soil. Soils weren't around in the beginning. It took millions and millions of years to form soils. So the Earth wasn't covered in dirt. There was no grass. It was just volcanic material. It was just rock. And then over time, oxygen, air, rain, stuff like that started to break down the rock to form soil. So there was no soil on this Earth day one. So that took time to form. Quickly, I'll go through the factors. Most of this is pretty simple. Things that affect weathering that are going to cause it to rocks to break down either quicker or slower. One is exposure. So the more the rocks are exposed, the faster they'll break down. So when you drive around, the roads around Rhinebeck, Slate Quarry, the Taconic State Parkway, the New York State Thruway, you see what are called outcrops, right? Out means exposed, right? Out. And crops just mean rocks that are exposed to the elements. They're not covered by dirt. They're not covered by trees. They're not covered by shrubs. So those are going to be the rocks that are going to break down the fastest, the ones up here on the surface. The rocks that are 200 feet below us are not going to break down, right? They're covered by soil and they're protected. So the more they're exposed, the faster they're going to break down. That's just common sense, I think. Here's some outcrops. So you drive around. These aren't from here, but you see this common in the Hudson Valley. You go into the Catskills. All these rocks that are sitting up here on the surface are going to be exposed to the rain, exposed to the air. So they're going to go through physical weathering, chemical weathering a lot faster. The rocks that are way down deep inside the earth, they're protected. They have a barrier, so they're not going to, it's going to take longer for them to break down. So they call these rocks outcrops. Particle size. So smaller pieces mean faster weathering because there's more surface area, right? They've already begun the process of weathering, but they're going to break down faster. I'll show you a diagram of that. So if I take this big cube over here, right? A cube has 6 sides on it. That's only 6 sides for which water and oxygen can attack. But if I take that cube and break it into smaller cubes right here, so now I've got twice the surface area. I've created smaller cubes. Each one of these has 6 sides, 6 sides, 6 sides, etc. That's more surfaces, right? More surface area. I can break down even faster. Or I go to this picture. I've got even smaller cubes. So each one of these is 6 sides. I've got more surfaces for water and air to attack. Or go even smaller. This is where I would have, well, if we were in school, I was going to do the Jolly Rancher lab with you, which is kind of cool. That was the one where I was going to divide you guys into 2 groups. Half of you would have gotten a whole Jolly Rancher, and half of you would have gotten a Jolly Rancher I smack with a hammer and crush into small pieces, and then we keep track of the time it takes to dissolve. So you'd pop it in your mouth, keep track of time that it takes to dissolve, and obviously you're going to know right now, and most kids knew beforehand, it was just a fun activity because it was candy. The people that had the crushed up Jolly Rancher, their times were a lot less, and the people that had the whole Jolly Rancher took a lot longer to dissolve. So that's showing this whole idea of surface area and weathering. Unfortunately, we're not in school, but if you'd like to go out, buy yourself a Jolly Rancher and test it yourself, please, by all means, do that. Composition. So, again, we talked a little about this with the headstones. If you have rocks that are made of harder materials, they're going to take longer to weather, or they're going to be what they call more resistant, whereas a rock that's made of softer materials is going to break down faster. Right? So, again, if you take statues and things that are made out of quartz, which has a hardness of 7, or granite, which is mostly quartz, those statues, monuments are going to be more resistant. They're going to take longer to break down. If you have rocks that are made out of things like calcite again, marble, limestone, they're going to be softer. They're going to be less resistant. So quartz and granite are going to be more resistant. Calcite, marble, limestone are going to be less resistant. They're going to break down faster. This was a Regents question. It was very easy. The key to it was to look at the surface up here. It said, which type of rock appears to have weathered and eroded the most? So the most would be obviously right here where you see that dip. So then you would say, all right, match up that picture, which happens to be shale. That's the universal symbol if you look in your reference table. So you would go to choice 3. This one took it the opposite way. So they showed you this column of rocks sitting out there exposed, and it said which rock is the most resistant. So they wanted to know which one was the toughest rock, which means you're going to pick the one that's sticking out the most. So you can see this right here, layer 3, which is sticking out the furthest, right? 2 got eaten away a lot. 4 was weathered and eaten away a lot, but 3 is sticking out the most. So I would go with 3 on that one. This is the fourth factor, climate. So again, if you need water, notice both need water. You got humid and humid. The difference would be chemical weathering, you want it to be hot. So you want to make those caves like Howe Caverns. You see a lot of caves actually in your tropical islands, your Caribbean islands. But that's because it's a hotter, more humid climate. So chemical weathering, you want the heat and the humidity. Physical weathering, to have the ice, to have that freeze thaw, you need both. You need cold weather to make the ice, and then you need warmer weather to melt the ice. So there's the difference between them. And then I have one more slide. This is just a summary. It shows you different places around the globe, and it shows you what type of weathering. So, for example, if you see letter D here, letter D is Poughkeepsie. And so that would put us right here. This graph shows 2 things. What's your average temperature for the year, and that's in Celsius, and what's your average amount of precip centimeters. So our average temperature is at about a little over 10 degrees Celsius. That probably puts us in like the 40s, 50s. So that's our average, right? We take winter and summer. And our amount of moisture is at 100 centimeters per year. That puts us in this section here. Moderate chemical weathering, which means we have some chemical weathering in the summer, but we also have the frost action. We'd be in the same category as letter E, let me clear this, which is Minneapolis. So Poughkeepsie and Minneapolis are both going to be in that. They get both. They get some chemical weathering with the physical weathering, the frost action. If you take a place like, we'll go way up here, letter B. All right, letter B is the Amazon rainforest, which you can see their average temperature is in the upper 20s Celsius. So you're talking, their average temp's probably in the 80s and 90s, right? It's always hot, and look how much moisture they get. They get more than double what we would get. They get 225 centimeters of rain. So it's hot and it's wet, and you can see where that puts them. Also letter A, San Juan, Puerto Rico, right? Your Caribbean islands, strong chemical weathering. Notice you don't have any frost action up here, right? These places, if you're up in this area where you get a lot of moisture and the high temperatures, you're only going to have chemical weathering. And then if you go to the opposite side of this and you go way down here, places like letter G, letter I, you're talking about Siberia, right, where it's extremely cold. Their average temperatures are below 0. They have not a lot of rain because remember, cold air is dry air, so not a lot of moisture. They get moderate frost action or slight frost action. But again, you notice over in this section, because it's so cold, you notice no chemical weathering. So you're not going to get any kind of chemical weathering until your average temperature is at least in this section above freezing, 0, 5, 10 Celsius and up. And then as you go from left to right, you'll notice when you get over here, all you're seeing is all chemical weathering, no physical weather, no frost action. Then you could take one more city, which is letter H. H is going to put you in Phoenix, Arizona. Hot, but notice very little moisture. Phoenix gets, and sorry, my mouse is not easy to control. You're talking less than 25 centimeters, and it's very dry, right? No water, no weathering. So that's why places like Phoenix, the rocks tend to be a lot more resistant, and they don't weather as quickly as they would, let's say, in Poughkeepsie, because of the fact there's very little water. So that's what this graph is showing you, a climate graph. So I'm just going to quickly go back and again show you the four things. Oops, too far. So you've got exposure, right? Rocks that are at the surface are going to weather faster. You've got particle size. Smaller sizes will weather faster than large pieces because of greater surface area. That's the reason why. You've got composition. Rocks that are made of harder materials are going to be more resistant. Rocks made of soft materials are going to weather quicker. And then you've got the climate type. Hot and humid creates chemical weathering. Cold and hot, freeze thaw with, again, humid creates physical. Both times you need water. Always need water for both. And that is that.